Stripping down science. The Naked Scientists.
Hello and welcome to The Naked Scientists, broadcasting from the BBC across the Eastern Counties. I'm Dr. Kat, and here we have Dr. Dave.
Good evening.
And also in the studio, we are looking at archaeology, ancient history. How do we find out about ancient cultures, ancient environments? What sort of ways can we study them? And we have some highly expert guests here. We have Lawrence Owens from Birkbeck College in London.
Hello.
And we also have Harriet Allen from the Department of Geography here in Cambridge. And we're also going to be joined later by Nick Brooks from the University of East Anglia. So stay tuned, and if you've got any questions about ancient cultures, ancient environments, what was the Earth like? Is it really changing? What were ancient peoples like? Get phoning in now, 08459 25 2000. You can text us 07786 20 1960, and you can always email us at chris@nakedscientist.com. So what else we got, Dave?
Well, if you're feeling like doing an experiment, me and Derek went into Hunsbury last week and we made a force field. All you need for this is just an empty drinks can and some polystyrene. And the prize, if you tell us what actually happens, will be a copy of Dr. Chris's new book, Naked Science.
Yes, we have locked Dr. Chris in a shed this weekend, so we're doing the show. Yes, if you want to win that fantastic prize, get phoning in. And also, this week we have a teaser question, which I've come up with for you. Right, so you think you know your space science, you're only good at constellations, we've got the Plough, we've got the Great Bear. I want to know, what is the brightest star in the sky? Is it the Pole Star? Is it Betelgeuse? What do you reckon? So get phoning in now and tell us what you think. Also, any questions, let us know.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
And now for the science news. Ken Teo and colleagues at Cambridge have made one of the most slippery substances known to man. It's 4 times more slippery than Teflon, which is the stuff you get on non-stick frying pans, and is really quite slippery.
Is it as slippery as bananas?
Considerably more slippery than even bananas, Kat. Yes. Okay, what they did was they made a little forest of nanotubes. These are little tiny bits of graphite rolled up into tubes, a bit like buckyballs, but in tubes. They made like thousands and thousands, all lined up in a little forest, and they discovered this is really, really slippery. They pushed around little polystyrene beads on it, and they could even push around really soft latex beads, which would stick to a normal surface, like even PTFE. So the reason why this is that if you have lots of little tiny a forest, the only bits which touch the beads are the very ends, and because there's such a small area touching them, there's very little to stick, and so they slip.
So there's no friction on the tubes?
Yeah, they've actually used similar things to make water repellent surfaces, because there's nowhere for the water to touch it, so the water can't stick to it either.
So what can we do with these nano surfaces?
Well, they're probably not going to be used on your frying pans very soon, because they're quite delicate still. But what they're really useful for is moving around very small objects around, because it's very hard. Because if you touch, they tend to stick to things because it's so small. And Kajel Geerder from the Technical University in Denmark has used these things, a bit like stickle bricks, to pick up delicate nanofibres, which would break if you push them around normally.
OK, so it's a way to do nanotechnology engineering, stuff like that. Oh, brilliant. I've got a completely unrelated story, which is to do with poplars, the trees that are probably growing around your house. And the scientists at the University of Ghent in Belgium have managed to solve the genetic code of the poplar tree. They've been looking at the DNA in these trees and have worked out all the letters that are in the information in the tree's DNA. Well, so why is this important? Well, about 6 years ago, scientists managed to work out the genetic code of a small plant. This is a type of cress called Arabidopsis. But so far, no one's managed to work out the genetic sequence of a tree. And this is important because trees are actually a lot different from plants. Trees do things like make wood, and we can use them to make biofuels and all sorts of things. And they're very, very good at taking out large amounts of carbon dioxide from the environment. And as we know, carbon dioxide in our environment is a bit of a problem at the moment. So now they've managed to track down all the information in these trees' genomes in the DNA, and they think they have about 45,000 genes spread over 19 chromosomes. And intriguingly, 10% of these genes are unique to trees, to the poplar, compared to the existing plants that we know of their genes. So these could be the genes that make trees like trees and not like cress. So hopefully we might be able to do genetic engineering on trees now we know what these genes are, and make them better at taking carbon dioxide out, or better at giving us biofuels.
I guess they don't understand what the genes do yet. They've just worked out what they are. They just read it.
Yeah, so we've got a long way to go before we really know how a tree works, but it's getting there.
Now, Dan Gervasi at Arizona State University has been looking at hydrogen fuel cells. The big problem with them, it's quite easy to make a fuel cell. The real problem is storing the hydrogen, because hydrogen's a gas, it's explosive, you can't squeeze it into a very small space. It's a very low-density form of power. Now, what they want, and it's also dangerous, so what they've done is they've taken something called borohydride, which is basically a boron atom, reacted with some hydrogen, which makes an alkaline solution. And a 30% solution of borohydride actually stores more hydrogen per unit volume than liquid hydrogen itself. And it's much easier to move around, it's not toxic, and it's not going to explode. Now, what you do is then you pass this over a ruthenium catalyst, which will release the hydrogen, and you just put it straight into your fuel cell. Theoretically, this could mean that you could get a fuel energy density of about 2,200 watt-hours per litre, which is far better than the best batteries you can get now, which are only about 200 watt-hours per litre. He's not quite got there yet. He has problems. The borohydride tends to come out of solution and gum up all of his pumps, and it's a bit of a pain. He found that if you add antifreeze to the mixture, it helps quite a lot. But he's still only got the energy density to 600 watt-hours per litre. That's still a lot better than the best batteries around.
So let's hope for that. And a final story is that some researchers now in America at the Fred Hutchinson Cancer Research Centre have found a reason why it really is good to exercise. And they've been studying the guts of people who do a lot of exercise and have found that they actually may be much less likely to get bowel cancer. Now, unfortunately, their research only shows that men can benefit from exercise. What they did was studied about 200 healthy people who hadn't really done that much exercise before, men and women, and they put them on different exercise programs. And the most heavy exercisers were doing about an hour's exercise 6 days a week. Some of them were doing about 4 hours of exercise per week. But they found that the most heavy exercisers, they had really significant changes in their gut. Their cells weren't multiplying quite so much, which can be a hallmark of cancer. It's when your cells start multiplying out of control. So, if you ever needed a better reason to get in the gym, that could be it. Protect yourself from bowel cancer.
Wow. Now, as I was saying earlier, me and Derek went to Hunsbury Park Primary School to build a force field. So if we go over to Derek now.
Hello there, welcome to Hunsbury Park Primary School, where we've come this evening for a fantastic science experiment which you can do at home, so please listen out. There's only a couple of things that you need, and I hope that you all have them at home, so do listen out for that. With me, of course, is Dave. Good evening to you.
Evening, Derek.
OK, and what have we got lined up today, then?
We're going to be building a force field just using a piece of polystyrene.
Force field, all right, wow, it's like Star Trek or something, fantastic. OK, then, and also we've got two guys who've come down to help and do the experiment as well, so guys, can you tell me your names and ages, please?
I'm Matthew and I'm 11 years old.
Hi, I'm Robbie and I'm 11 years old as well.
OK, thank you very much. So, Matthew, I mean, we're going to do some science today, so what do you like about science, if anything at all?
All the inventions they do.
OK, then. And what about you, Robbie?
Human organs.
Oh, human organs. Wow. OK, that's pretty cool. All right, then. Well, I think we've got a kind of invention here that Matthew might like. We've got a force field that we're going to be making. OK, then. So what you need at home, if you'd like to do this, it's very simple. Firstly, you need a big bit of polystyrene, if you've got one. Maybe some packaging from a cardboard box or something. That would be fine. Also, you can use a blown-up balloon if you want to. You need something to create static, and we'll be explaining more of that later. Also, you need an empty fizzy drinks can, an empty Coke can, whatever. That's fine. If you've got one that's full, get it down you and make sure it's empty. And finally, you need somebody's head, OK, with hair on it, if that's all right. Hairless heads won't really do. So we need somebody's head, and hopefully one of these guys, Matthew and Robbie, will be volunteering their heads for us. OK, that's cool. So, Dave, what do you have to do then? Please instruct these guys and also the people at home.
Well, the first thing you do is you take your polystyrene and you rub it on some hair. It doesn't really matter what kind of hair. Traditionally, you use cat hair, but it's probably easier to use your own or somebody else's. A woolly jumper will work quite well as well. So just take the polystyrene, rub it on there really well, and then just put it near the fizzy drinks can and see what happens.
OK, and do you just leave it near it or wave it around or what?
Wave it around near it and see what happens.
OK, then, there you go. So you've just got to get this piece of polystyrene and, of course, a balloon as well. That will do, will it?
Yeah, a balloon, something like that, sort of plastic light sort of things generally work well.
Yeah, OK, then that's cool. So you've got to rub that on your head quickly as you can and then wave it around near your empty Coke can. And it's got to be done on a kind of a flat, smooth surface as well, and like a tabletop, and just see what happens. Now, Matthew and Robbie are here listening to that. Firstly, we need a head. We're going to do it later, but who's up for using their head today, do you think? Oh, they're both putting their hands up, but Robbie more enthusiastically. OK, why do you want to rub this on your head, Robbie?
Because it's comfy.
It's comfy. Oh, fair enough. OK, we shall see if you agree with that when we actually do it later in the show. Matthew, though, what do you think is going to happen when we actually wave this kind of polystyrene next to the Coke can after rubbing it on Robbie's head?
It's going to push the Coke can further away from the polystyrene.
Oh, OK. Dave's smiling. He's well, I don't know. He knows what's going to happen, so we'll find out. Anyway, if you'd like to do this at home, you can, of course, win a prize if you do it and you tell us the right result as well. So please do so. The number you can call is 08459 25 2000, and you can also email chris@thenakedscientist.com. And so please do come back here to Hunsbury Park Primary School later in the show when we'll be doing this and also getting the usual explanation from Dave. OK, that's all then. Back to you in the studio.
And that was what Derek and Dave got up to on their holidays. So we want you to try that at home if you get your Coke can, your piece of polystyrene, and get rubbing, I suppose. And the first person who calls in with the right answer is going to win a copy of Dr. Chris's new book, Naked Science. Also, get phoning in if you have any questions for us. We have guests in the studio tonight who are looking at how things used to be. What were our environments like? What are our people like? If you've been on holiday somewhere to go and look at an ancient civilization or some ruins or something, have you ever wondered, how do we know about how these people lived? How do we know what their environment was like? So if you want to know, get calling in now, 08459 25 2000.
The Naked Scientists, supported by the Wellcome Trust.
And we've had a question in on the email who's from John Berger. And he says, right, he's got a question on electrical power generation. He's watched the NASA astronauts going through all this trouble, delivering and installing solar power generators on the space stations. And he wants to know is, why haven't they been clever and hung a couple of electrical cables from the space station and let them generate electricity by moving across the Earth's magnetic field? Because normally a generator works by moving a magnet through an electric field. You can make current. He says, well, this would be far less expensive than solar panels, so why don't they do it? Dave, why don't we do it?
Well, you can, and they have tried it. Basically, what you want to do is they've made a big, long wire, maybe a couple of kilometres long. They've hung it from the shuttle, I think it was, and they've tried to generate power using it by moving it through the Earth's magnetic field. The problem is it's actually very difficult to manoeuvre a 2-kilometre long wire in space, because if you start a little wave going along it, there's nothing to stop it. There's no air to damp down the vibrations, and you get very complicated interactions between the magnetic field and the wire. And so they can and they have, but it's a lot easier to put up the other problem is it takes the energy out of the orbit. So it'll mean that the satellite will come out of orbit quicker, which is okay for the space station because it gets up and pushed regularly. But it's not ideal for the space shuttle especially, but it's not ideal for for a satellite which wants to stay up there for a long time. So they have done, but it's a lot easier to just use a solar panel.
So that's your answer, John. I hope you like that.
And now another question. Well, let's give it to you, Kat.
It's a question
for you, yes. Okay, this is from James French. He says, could you please explain to me the very basics of string theory? I failed Lego at school. I'm not very technical, but even string theory for dummies was beyond me.
Right, so we're asking a biologist to explain string theory. This is going to be very simple. String theory is a way of looking at the world to try and work out what we're made of. You may have heard that we're all made of atoms, and atoms are composed in turn of other little bits. There are electrons, neutrons and protons. And if you break it down even further, things like neutrons and protons and stuff are made up of really tiny particles, and these are called quarks and leptons. So they have cool names. And quarks and leptons and electrons, neutrons and protons are what makes up stuff. And there are different forces that can act on stuff to make things move or to stick together. And these are gravity, electromagnetic force, so that's magnetism, electricity, and there's something called the weak and strong nuclear forces, which sounds a bit Jedi to me. But these also help to stick stuff together. And we have a standard model of how you explain stuff, which is all about, well, there's quarks, they stick together. We have electrons, atoms, they all stick together. But what you can't really explain is how gravity actually works using this kind of model. And so some very clever maths bods have been trying to work out if you can come up with a new way of explaining how gravity works, using the bits that we have. And they've come up with string theory, which says that all these tiny bits of stuff, so the quarks and the leptons and everything, they're actually like a tiny piece of string that wiggles around in all sorts of different ways. And it depends how you're seeing that particular waving string. So if it's waving in one particular way, when you look at it, you'll see a lepton of some description. And if it's waving in a different way, you'll see it as an electron. So everything is just little waving bits of string. And apparently this can explain gravity. So I really hope that makes sense. You can find out more at superstringtheory.com, apparently.
If it's any help to you, no one's actually found any evidence that this is the case, because all the things it predicts happen at so high energies that we haven't actually been able to look at them yet.
So we could just make anything up. The world is made of jelly and it just vibrates everywhere. That's my impression of it. Okay, what have we got coming up next? We have some guests in the studio. We have here with us Lawrence Owens, who can talk about ancient civilizations. We'll hopefully find out some gruesome stuff about Peruvians. Also in the studio, we have Harriet Allen, who's here from Cambridge University, to talk about what do we know about ancient environments, ancient trees and plants. What was our world like about 10,000 years ago? And we'll also be talking to Nick Brooks to find out more about deserts and the sort of pressures that brought societies together when we were all roaming around in the desert.
Now, it's a time of the show where we go over to the States to hear the news from the Science Update team. This week, Bob and Chelsea take a look at sound, including music from Mount Etna and noise pollution in the oceans.
This week on Science Update, noise pollution is now a problem in seas as well as in cities. But first, Chelsea has a much more pleasant noise to play for us, and you'll probably be surprised by its origin.
If a volcano could play piano, this is what it would sound like. Physicist Domenico Vicinanza of CERN in Switzerland created the music by converting a seismogram from Mount Etna into a musical score.
If the volcano is quiet, the melody is confined, is bound in the middle part of the piano. As soon as the volcano oscillation is becoming larger and larger, so the volcano is becoming louder and louder, the melody starts to scatter up and down, reaching higher notes and lower notes.
So how will this help? Vicinanza says people are often better at picking out patterns by ear than by eye. So this technique could help scientists find patterns in seismic activity across many volcanoes.
Our aim is to use all the recorded data and try to understand what happens when the volcano starts to become louder and erupts. So we can say which is the signature tune, the signature melody that can be taken as the signal for an imminent eruption or in an imminent earthquake.
He adds that this technique could prove useful in analyzing data in other fields, from stock market numbers to patterns in language. He also hopes it will be welcomed by musicians as a new way to create nature-inspired tunes.
Thanks, Chelsea. Well, here's another tune of sorts, but one that's not so welcome. It's the sound of a ship underwater. Scientists think it might interfere with how whales and other sea mammals communicate and find food. Now a team has discovered that ambient underwater noise has increased 10 times since the 1960s, at least in the Pacific. But it's not just that the number of ships has gone up. John Hildebrand of Scripps Oceanography says traffic has only doubled since that time.
So a very significant part of the increase comes from the fact that the ships themselves must be generating more noise. The ships are bigger, they travel faster, they have greater total tonnage that they're transporting.
Hildebrand and his colleagues were able to do this analysis because they found declassified Navy reports from the 60s on the ambient noise in the Pacific, part of the Navy's Cold War defense. They were then able to make recordings in the same spot and compare them. Although it's not hard to prove that noise has gone up, he says what is hard to prove is that it's having an effect on the mammals.
The insidious thing about this is that the ambient noise has been increasing at probably a fairly steady pace. So there wouldn't be some dramatic event where all of a sudden the marine mammals, would be doing something differently. It's tricky to figure out what the impact really has been.
But he says it may not be as hard as it might seem to convince the shipping industry that noise is a problem. Quieter ships would be better for the crew and should be more energy efficient. He adds that in looking for a solution, scientists may again turn to the Navy, who are, after all, experts in being quiet underwater.
Thanks, Bob. That's all for this week. Next week, we'll talk about some ants that do some amazing acrobatics. Until then, I'm Chelsea Wald.
And I'm Bob Hershon for AAAS, the Science Society. Back to you, Naked Scientists.
Thanks, guys. If you want to hear more from Bob and Chelsea, you can do so by checking out their new website at www.scienceupdate.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Here we have in the studio Lawrence Owens from Birkbeck College and the University of London. Hello. Now, I've heard that you've been to some really exotic places. You've been to Peru and Bolivia, and I'm of the opinion that scientists go to places like that because they fancy a bit of a holiday. But apparently you've been doing some work. So what have you been up to?
I have been doing some work, yeah. I was very lucky a couple of years ago to go to Peru to analyse some mummies they discovered near Lima, near the capital. And I've been there going there for the last 2 summers now, analysing all the remains of up to 80,000, we think, burials from this huge site we have.
So are these mummies like Egyptian mummies, sort of wrapped in bandages and stuck in a tomb?
It's that kind of thing. I mean, they're a bit slack about doing mummies in Peru, it's got to be said. I mean, in Egypt they did all kinds of things. They sucked the brain through the nose and all kinds of horrible things. But in Peru, they just kind of buried them in a rather slack sort of way. But being Peru, it's quite dry, so they preserved very nicely.
What can we find out about ancient Peruvians? How old are we talking, these civilizations?
Well, these ones vary from the Incas, which are fairly recent, around about 1400 AD, back to about the 2nd century AD. But of course, mummies in Peru go back much earlier than that. My site is just that period. But you can learn virtually anything you can learn from someone, just talking to them, you can learn from mummy, because your body, your bones, your teeth, they betray you completely. Nothing is sacred.
So what sort of things have you found out, and how do you find it out?
All right. You can tell, for example, exactly where somebody is from. You can tell it from their teeth and the shape of their teeth and their skull, and you can look at things like, for instance, the isotopes in their teeth, and then you can look at the content of their bone and collagen, and you can figure out what part of the world they came from. You can look at their health during their life, how sick they were when they were children, the diets that they had, how they met their demise, of course, and all kinds of things like that. Virtually nothing you couldn't find out from someone.
And can you find out what they might have done, what sort of occupation people had?
Yeah, we found these massive guys who are obviously into construction and so on, and they're huge and brawny arms. I mean, we made Arnold Schwarzenegger just pale and insignificant. These guys were massive.
Peruvian builders, basically.
They were massive, like pyramid builders from Egypt, the same kind of thing. They were really huge as well. And then you have people, for example, people who used to do sewing on ceramics. They have unusually strong hands, and we know they worked with these things because they're buried with the tools of their trade, and so everything's actually buried with them. And so you can work out also some very tragic stories, like we found people who have actually died in childbirth, and we know how old they were, and so we can tell you about 15, 16 years old. It was a very, very common time to have children back in the olden days in Peru. And so there's virtually nothing you can't find out.
Well, we've had a call in here from Anne Delivote, and she says that she was in Peru a while ago and saw an ancient ceramic pot from the Moshe culture with a very gruesome decapitation scene on it. And she wants to know, were these ancient civilizations actually really bloodthirsty and violent? Or is this just, a little cultural thing like the equivalent of our video nasties? So, we hear about them cutting up people and being really gruesome. Is this true?
Well, you see, they did do it a fair amount. The Moshe are actually one of the most epic examples of this sort of thing you can find in the world ever. I mean, some cultures did it to a certain extent. They had sacrifices in a rather more modest way. The Incas used to bury children on mountaintops and so on. I'll come back to that shortly. But the Moshe were really, really sanguineous. They had a little tiny area on the coast of Peru, northern Peru, and they hacked it out of virtually nothing. And so it was a very, very small area, lots of canals and agriculture, and the society was very, very rigid, and they would go out and fight with neighbouring tribes and nick all of their land and so on. And then they would ritually decapitate all of the captive men. And they may keep some of the women, but not very often. And they would hack them. They would cut off their arms, and they would remove bones from their arms while they're still alive. And then they would smash bits of them off, and they would throw them off these cliffs into this enormous pit, and then leave them there for the vultures to eat. They were pretty nasty. And they even had a deity called the Decapitator God, who had a giant eagle-like head and a huge, nasty-looking blade in his hand, and he would rush around the place, decapitating all these poor, unfortunate captives.
Wow, I think you've answered Annette's question more than she could ever have imagined.
Yeah.
So how do different cultures, even in Peru, how do you find differences between them? Are there very distinctive cultures?
Well, that's the thing, you see, about cultures. What's a culture really mean? And, of course, it's very hard to define. But these groups lived in a very, very defined area, and very often their habits just developed in a very specific direction. And so, for instance, the Nazca, you must have seen the Nazca lines, those enormous things on the desert, big lines and patterns and drawings and so on. Now, people down there, they had a terribly hard time of it because it was so desiccated and very, very dry. And so they used these things as kind of a magical ritual way of getting it to rain. And then other parts, say the Incas, they were massive empire builders, and they built thousands of roads going all the way across the nation. The Moshe I already mentioned, and there are dozens of other little tribes and groups. And then, of course, people in the Amazon, all living their different ways. And so they were very distinct. And, of course, we're talking a very long period of time as well.
Well, we're going to be talking to Nick Brooks later from the University of East Anglia, and he can tell us more about how societies form under these kind of pressures for resources, and also how societies have survived in the Sahara. But also we have here Harriet Allen, who's from the Department of Geography here at the University of Cambridge. And I understand that you're studying the environment of Portugal.
Yes, I'm interested in the way ecosystems change over time, and that could be thousands of years, or it could be even over shorter periods of time.
So what's the environment like now in Portugal, and then how was it, say, 10,000 years ago?
Well, in common with many other Mediterranean landscapes today, the vegetation is very much dominated by shrubland communities, which are extremely well suited to the hot, dry summers and the cool and relatively wet winters. Whereas about 10,000 years ago, you would have had a more deciduous type of vegetation, many more trees probably in the landscape than we would see today.
So big sort of leafy trees, like
deciduous. Well, not so much chestnut, because many of that has been imported from the eastern end of the Mediterranean towards the western end of the Mediterranean. But there would have been many more deciduous oaks and other taxa.
Well, how do you know that this change has taken place? I mean, we only see the trees we've got now.
Well, there are certain types of environments, such as wetlands, where we can extract material which dates back over thousands of years. So we can use sediment cores, and we can go down a metre at a time and retrieve the material, take it back to the laboratory and analyse small quantities of it and see what pollen has been preserved within the sediment. And by looking at the pollen, we can identify the different, sometimes species, but more often the genera or the families from which the pollen has come. And from that, we can reconstruct what the vegetation was like.
So you're just actually looking at the pollen grains, and you can recognise all different kinds of pollen grains?
Yeah, pollen grains have different types of ornament depending on the species, and so some of them are some of them look a bit like medieval instruments of torture because they've got large spines sticking off them. These are large in the context of being microscopic, of course, and they may come from some of the more weedy species, such as you find in the daisy family. By complete contrast, if you look at something like pine pollen, coniferous pollen, it has S-sacs, and these S-sacs, if you imagine Mickey Mouse's face just for a moment, the face is the basic part of the pollen grain, and Mickey's two ears are the S-sacs, which help to make this particular grain very buoyant, and so it's well dispersed. And so different types of pollen have ornaments which are relatively easily identified under the microscope and allow you to then identify the grain either to the species, usually to the genus, and sometimes only as far as the family level.
But how do you know how old these things are? Are they fossils, or are they the actual pollen?
Well, technically for the last 10,000 years, no, they're not fossils. We might refer them to as subfossils, but they are the intact grain which has been preserved in the environment. So they've been washed in or blown in, incorporated in the water, and then settle out through the water column and incorporated into the sediment which accumulates, say, at the bottom of a lake.
But how do you know how old a pollen is? I mean, it's just in the mud, isn't it?
Well, it is just in the mud. And in a sense, you can't actually date the pollen, and what you're dating is the material in which the pollen is found.
So the mud.
So you're dating the mud, yes. Or it might be a peat bog, or it might be in a riverine environment where you've actually got sort of more siltian conditions, or sometimes gravel conditions. And to some extent, it depends on how much organic material is available. And if you've got quite a lot of organic material, then you can use radiocarbon dating, and that will then give you some dates.
Do you see kind of big major events in the pollen record, so like volcanoes and things?
Well, you don't tend to see that in the pollen record, but you tend to see that within the sedimentary environment. So I've got some colleagues who work in Greek lakes, and they find layers of ash which have come from some of the Italian volcanoes. And if you know what the chemical signature of the tephra, the ash, is, you can then identify which volcano it has come from. And by extrapolation from other sources, knowing the date of that, you can then try to ascertain the date of which it was deposited within the lake.
So to go back a little bit, you've said that over the past 10,000 years we've seen quite a dramatic change in even just a country like Portugal. What sort of things have caused that change in the climate, and are we still seeing the climate changing again and affecting the environment?
It's a bit of a tricky question to answer because no two people will necessarily give you the same answer with respect to somewhere like Portugal or other Mediterranean countries, and it rather polarises between those people who think that the vegetation has changed because people have changed the landscape and those people who regard it as evidence of climate change. And somewhere around about sort of 5,000 to 6,000 years ago, there are suggestions that the climate became quite a bit more arid, and at that time you moved from the deciduous taxa to the more evergreen taxa. But other people argue that that was probably the result of people clearing the landscape for agriculture, and the soils degraded, and so when there was recovery of any vegetation, it was less likely to be the deciduous taxa which came back in, but more the evergreen taxa. And there's some suggestion that there was sort of a slow spread from the eastern Mediterranean towards the western Mediterranean, which might have matched the timing of agriculture arriving from the eastern Mediterranean towards the west, and then obviously towards the northwest and to the UK.
And to sort of extrapolate a little bit to the UK, we know that the climate is changing. It looks like things are getting warmer. Do you think we'll see the sort of trees that we have in the UK changing? I mean, we have our big oak trees and chestnuts and things. Could they be doomed?
I'm not sure about doom. There are some suggestions that gardeners ought to be changing the species that they're growing in their gardens, and on the radio this morning there was a suggestion that people should start to grow olives, and that maybe in a few years' time olives will be a crop which you find within the UK. I think it's being grown on an experimental basis down in Devon at the moment, but I think it's very likely that the vegetation will change in response to the climate changes that we're seeing.
Sorting out the sparks from the quarks. The Naked Scientists.
You're listening to The Naked Scientists, and we're talking about ancient civilisations and ancient environments. And joining us now, we have Nick Brooks from the University of East Anglia. Hi, Nick.
Hi.
Hello, good you're there. I understand you're a bit jet-lagged now.
Just a little bit, yes. I've just returned from New York yesterday. So.
Well, you work in a slightly different environment from New York. I understand you work in the desert. What can you tell us about that?
Yes, indeed. Well, whenever I get the opportunity, I sort of pursue my own field research, which is, at the moment, focused on Western Sahara. Prior to that, I've done quite a bit of work in Libya as part of a much wider project called the Fazan Project, examining the interaction between past climate and environmental change and ancient civilizations.
So when we think about the desert, you think of something that must have been desert for absolutely thousands of years, but this isn't always the case with the Sahara, is it?
That's true. The Sahara has actually gone through a number of humid and arid phases that pretty much fall in step with the glacial cycles. And the last humid phase in the Sahara lasted from about 10,000 until about 5,000 years ago. And during this period, the desert as we know it today was actually more like a savanna environment with open woodland and lakes and rivers.
So what sort of different cultures and animals and things would we have found there compared to what we have now?
Well, we actually have some very good records that the prehistoric inhabitants of the Sahara have very kindly left us if we want to see what they were up to and what the environment was like. Archaeological studies tell us that the region was re-inhabited as it became more humid about 10,000 years ago by hunter-gatherer groups. But later we find the emergence of cattle-herding societies and then later some sedentary societies such as the Garamantian civilization in southwestern Libya. And the environment, as I mentioned, was very much like savanna, woodland, much like the environments you'd find in southern Africa today. And we also have millions, literally millions of rock art of paintings and engravings that depict the large humid climate African fauna that we find further south in the more humid regions now.
And so the civilizations that we find there, we've already heard from Lawrence today, who's told us about the sort of cultures did things like killing each other because there was a fight for resources and they wanted to keep their stuff for themselves. Do you see similar things as the environment's changing in the Sahara?
The Sahara is actually, although it's not famous, apart from obviously Egypt, for its large ancient civilizations, it is actually a very good place to study these sorts of processes because it's essentially a laboratory of adaptation. You have very, very clear and very, very extreme changes of environment and climate, and people obviously respond to those. We know that the places of parts of the Sahara that are now uninhabitable were, quite densely inhabited, relatively speaking, in the past. There's literally archaeological material scattered all over the desert surface. So yes, we can actually see how people responded to these changes, and one of the things that seems to be happening as the environment becomes more arid is people are becoming more territorial, and it appears that we have an increase in social stratification. This is evident largely through burial monuments.
So do you think, in the same way in Peru, do you think they might have become more bloodthirsty or more competitive?
Obviously, there would have been competition. You're talking about a landscape that was, widely inhabited, but then desiccated, leading to the emergence of a very small number of environmental refugia, where there was still water and pasture available. And people naturally would have either migrated out of the Sahara, and there's evidence that people moved south with the retreating monsoon. But also, we know that people congregated around diminishing lakes and oasis regions. So obviously the population density in these regions increased, and there would have been more competition for resources. Whether this expressed itself in a particularly violent way, and we don't really know, that's not that apparent from the archaeological record. No doubt there would have been some conflict, but we also know that people adapted their livelihood strategies and their social systems in order to survive in these smaller regions where different techniques and innovations were required.
So do you think it may have brought civilizations together to form bigger societies?
I do think, certainly in the Sahara, if we look at the emergence of the Garamantian civilization, there's evidence that this did emerge through a process of adaptation to an increasingly arid environment. And what you really have is the development of an irrigation-based, largely urban society emerging in one of these environmental refuges, as far as we can tell, through a pretty clear process of response to environmental change. And I do think this is a model that seems to hold in other places. For example, it's not that controversial these days to suggest that the rise of dynastic Egyptian civilization was largely influenced by the desiccation of the surrounding desert and the social changes that engendered. So, as for more bloodthirsty,
we don't know.
Certainly we saw the emergence of urban societies with governments and organised armies and increased organised warfare as these large urban civilizations developed against the backdrop of increasing aridity in many parts of the world, yes.
So we've seen the Sahara getting much drier, and as I talked briefly with Harriet, our climate does appear to be changing. How do you think societies are going to adapt for the changes we're going to have in the future?
Well, that's very, very difficult. I mean, recently when I was away, I was actually at the United Nations trying to do some work on adaptation. Obviously, there's a big problem with how humans are going to adapt to future climate changes, and we have a lot of difficulty with this. It's not a trivial problem. We can certainly say that societies will change as a result of responses to climate change. But it's interesting that if we look back in the past, most adaptations to climatic environmental change seem to involve things like population movements and migration. Now, these are options that aren't really that viable today, so we're going to have to look for other means. And I think if we have very, very large changes in climate, as are probably going to occur by the end of this century, then there will be a problem.
Okay, well, thanks very much, Nick. If you've got any questions for Nick, for Harriet or for Lawrence about ancient civilizations, how things have changed, where do you think we might be going in the future, get calling in now, 08459 25 2000. You can email us, chris@nakedscientist.com, and you can also text us, 07786 20 1960. And don't forget the teaser, what is the brightest star in the sky? We've got Richard in Ramsey who says the North Star. I don't think you're right, but we do have some people in the hat already, so do get calling in for us. Anyway, we're going to go now and hear from Clive Finlayson, who had a paper out this week in the journal called Nature. And he's been looking also into the ancient past. He's from the Gibraltar Museum, and he's been looking at our ancient relatives, the Neanderthals. They were once widespread across Europe, but were thought to have disappeared about 30,000 years ago, so that's even earlier than the civilizations we've been talking about today. However, no one really knows why. They were here, then they were gone. So Clive's been doing excavations in a seaside cave overlooking the Mediterranean, and he thinks they may have hung around for a lot longer than we thought. But in fact, as we've just discussed, the climate may have got the better of them.
What we found in a cave called Goran's Cave here in Gibraltar, facing the Mediterranean Sea, is a series of levels of human occupation. And the Neanderthals that have been occupying this site since 100,000 years ago continue to do so much more recently than people had expected. There are places where they were making their tools, left their tools, hearths, the food that they were eating, and we've been able to date this very accurately with radiocarbon dating to at least 28,000 years ago, but very likely much more recently than that, perhaps as recently as 24,000 years ago.
How do you know that what you're looking at is definitely Neanderthal in this region?
Well, Gibraltar, for a start, has almost a tradition for Neanderthals in the sense that a skull was found here in 1848. 8 years later, one was found in 1856 in the Neander Valley in Germany, and named Neanderthal, hence the term. So perhaps the first one was actually found in Gibraltar. Another skull was found in 1926, and in all we have 8 caves with evidence of Neanderthal occupation. The tools that they made, which archaeologists call Mousterian, are very characteristic. I'm talking of tools made of flint and quartzites in the shape of stone points to be hafted onto spears, cutting tools for defleshing and so on. They made these very, very identifiable and very, very specific and characteristic tools. So here in Gibraltar we have evidence of those tools in these layers that we've found, but also close by we actually have from the 19th century at least 2 fossils in 2 caves. So we are very confident that we've had a long period of Neanderthal occupation, and one that meant their survival until much more recently than we had thought.
And is that the major implication, or are there others on the basis of what you found?
Well, one of the things about the cave is the richness of the fossil material as well as the archaeological material. The levels of occupation are rich in fossil mammals, birds, reptiles. There's also pollen that we've been able to extract, and of course charcoal from the fires, and that has allowed us to make a reconstruction of the landscape outside the cave. If you go to the cave today and you look outside, there's a beach and the Mediterranean Sea. But for much of the period when the Neanderthals were living there, the climate was significantly colder globally, and the sea level was down by between 80 and 120 meters below the present level. This exposed a huge area of sandy plains, which I could probably best describe as a Mediterranean Serengeti. It was rich in herbivores, and the Neanderthals were eating them. And we know that because we find in the bones evidence of the cut marks made by their tools. We suspect that their diet is probably quite diverse. There's a lot of bird species being found there, so it's almost certain that they were eating ducks and partridges, but also marine material, mussels and marine mollusks, quite possibly also fish and seals. And then the vegetation, which we can infer from the pollen. So this allows us to do a climatic and ecological reconstruction. And what seems to be coming through is that this was one of those perhaps localized, privileged spots because of the benign climate that perhaps contributed significantly to this late survival. So I think it goes beyond just the issue of late survival and possible overlap with modern humans. It also suggests reasons why it was that they survived.
So the cave gives you enormous clues about when these people were there and up until how recently. But does it tell us anything about where they actually went and why they may have disappeared?
Well, part of the work that we're conducting at the moment, we've been collaborating with colleagues who are looking at deep sea cores of the Mediterranean. And around 24 or just after 24,000 years ago, there seems to be a very sharp signal of a climatic deterioration. It seems to involve cold conditions and particularly conditions that may be arid. So it could be that these last surviving Neanderthals lived in very small populations. They were, after all, the last ones. And any slight environmental change, perhaps a famine over a period of years caused by drought, may well have tilted them over the edge, never to recover again.
Well, that was Clive Finlayson from the Gibraltar Museum, and he was talking to Dr. Chris, and that was from the Nature podcast, which you can find at www.nature.com, and that covers all the stories from the week from one of the top science journals in the world, so you can hear even more of Dr. Chris if you go there. Now, we've got a call in from Mike in Malden. Hi, Mike.
Hello there.
Hello. What's your question for our scientists?
Well, for starters, did Atlantis actually exist?
Well, what do you reckon, Lawrence?
Atlantis. Well, the myth of Atlantis, or myth or story, is based upon a gigantic slip of land into the Atlantic or possibly Mediterranean, which contained a civilization which was privy to all kinds of information we no longer have. Now, so therefore, we've got 2 questions. Yes, there is evidence of slips in the Iron Age, as a matter of fact, in the Mediterranean, particularly around Turkey. But when it comes down to whether or not we've actually lost information which mankind would really benefit from today, that's a bit more difficult to demonstrate, unfortunately.
So maybe is the answer. Any other questions?
Well, yeah, there's 2 or 3 actually.
You can have 2.
There's supposed to be a cave in France that actually showed planets, a cave drawing that was drawn about 33,000 years ago, which I take it is Bronze Age. Something like that.
No, that's Upper Paleolithic. That's a very long time ago indeed.
Right, well, they're supposed to show planets that weren't discovered until the 1950s. Is that true or not?
Well, people have interpreted it like that. But I mean, most of the cave paintings are so bizarre that no one's really quite sure what they mean. So you have animals, which seem fair enough, and then you have all kinds of demonic creatures, and then you have people with ducks' heads and so on. So the planets thing is one possibility, but there's it's rather a slim one, unfortunately.
Yeah.
Okay, there you go, Mike. Do you want to have a go at our quiz?
Yeah, okay.
Okay, we're going to ask you some questions. The call of the humpback whale is louder than Concorde. Is that fact or fiction?
It's probably fact, though. Oh, it certainly travels further anyway.
Yep, the humpback whale is the world's loudest living creature and can be heard from 500 miles away.
Pretty good going. Next one. The longest python in captivity is 10 feet long. Fact or fiction?
I would think that's fiction. It's got to be longer than that.
Yep, you're right. Fragrant Flower, the python, measures 48.5 feet or 14.85 metres from head to tail.
Yeah.
That's a rubbish name for a snake, I have to say. I wouldn't call a snake Fragrant Flower. I'd call it Fang or something like that. Anyway, final one. A chicken can lay 1,000 eggs during its lifetime. Is that a fact or fiction?
No, that's fiction.
Well done. The average chicken manages a modest 300 eggs in its lifetime.
You've got 3 out of 3 there, Mike. So if anyone else can do better than you, then they probably won't. All right, thanks very much for your call.
Thank you.
OK, we also have a call now on from John in Colchester. Are you there, John?
Yeah, sure.
Hello, what's your question for us?
Did oil or natural petroleum deposits really come from primordial forests?
Wow.
With the thousands of barrels of oil taken out every day, there must have been an awful lot of dinosaur khaki and an awful lot of trees to make all this oil.
Right, let's ask Harriet this. Where did oil come from and how did we manage to get so much of it?
OK, oil is the rotten remains of trees and other vegetation. If you go back to the time of the oil-bearing strata that we find, or certainly the coal-bearing strata that we have in the British Isles, back to the Carboniferous period, the British Isles as such didn't exist as we would recognise them today. They were significantly further south towards the equator, and therefore we had a much more tropical climate. The nature of the vegetation would be similar, but not identical to perhaps modern tropical rainforests. And then as they fall down and the vegetation, the trees die, and as they fall down, they get buried over long periods of time, they get compressed, and ultimately that starts to form oil. This is not really linked to the dinosaurs, however.
So we're talking before the dinosaurs?
Yes.
But how come so much oil is there? And have you heard the idea that it might have been the sea from a methane designed asteroid that crashed into the Earth?
What do you reckon, Dave?
I think quite a lot of oil is also made from deposits in the sea. I mean, algae from the sea can go down and then it gets cooked. When it gets buried really deeply, it gets hot and it gets cooked, and it gives off oil which floats up nearer to the surface. But I haven't heard that it's from meteors coming down at all. No, I'm afraid not.
No, that's not something I've come across either.
OK, John, we're going to ask you some questions now. Do you want to do the quiz?
Sure.
OK, the average person in England can expect to live for 2.5 billion seconds. Is that true or false?
True.
Yeah, well done. That's about 78 years.
This is a great one. If you arranged all the ants on Earth, nose to tail, you could produce a line of ants 126 light years long. Is that fact or fiction?
I have no idea. I'll say fact.
Yeah, well done. We think there are 300 million trillion ants on Earth. That's 3 followed by 20 zeros, which is quite scary.
That made the oil.
That's pretty good going. And finally, the average person in the UK eats 10 kilos of chocolate a year. Is that fact or fiction?
That is £30, isn't it? 25 pounds. Average person.
That's about the weight of my leg, as far as I can work out.
I'll go for it, fact.
Yeah, well done. Brits snack their way through. Actually, so it's about 9.3 kilograms of chocolate per person per year, which is scary.
I think I eat all the chocolate. All right, well done, John. You got 3 out of 3, so it's going to be a face-off against you and Mike. Thanks very much. You're listening to The Naked Scientists with me, Dr. Kat, and Dr. Dave, and we're talking about ancient civilizations and stuff like that. But we do have a caller in now who is Brian in Royston. Hi, Brian. Nope, he's not there. He's gone. Anyway, he says he wanted to know, if we lose gravity, what will happen? Will everything fly up in the air? Dave?
Well, I guess he's asking what happens if the Earth suddenly didn't have any gravity anymore. I guess the first thing that would happen is at the moment the atmosphere is compressed by its own weight. It's being squashed down onto the Earth at great pressure, which is why there's any air to breathe. First thing that would happen is that would expand very quickly and fly out everywhere. And that might blow you up into space. If it wasn't for that, there's no particular reason for it to fly away. You just sort of sit there and gently get pushed around. But I think the first thing that would happen, you have a huge explosion with all the atmosphere disappearing, which would blow you up into the air.
OK, that's pretty dramatic. Anyway, we hope that you've all at home been making your own force fields using a piece of polystyrene and a Coke can. So it's time to find out from Derek what actually happens.
Hello and welcome back to Hunsbury Park Primary School. We are indeed still here, waiting to do the experiment with the bit of polystyrene and the empty Coke can, and we're all raring to go. So, Dave, shall we do it?
Yeah, let's.
OK, right, so please instruct Matthew and Robbie what to do.
So, Robbie, if you'd like to take this piece of polystyrene and rub the end of it on your head really well.
OK, and why not tell us how it feels as well? OK, here he goes. Is it comfortable?
Yeah.
Oh, OK, that's what you predicted earlier. OK, is he doing it enough, Dave?
Rub all over it. Get a really good rub all over your head. That sounds good.
OK, now immediately, what have you got to do now?
I think if I give it to Matthew, and if Matthew wants to poke the end which he's just been rubbing near the Coke can.
Oh, what happened there?
It came towards the polystyrene.
OK, so, and now when you pull it, what's happening?
It follows it.
All right, so, yeah, Robbie, what have you seen? What's happened?
The Coke can started coming towards the polystyrene.
OK, so what we've managed to build then is this kind of bit of polystyrene which we've been rubbing, and then when you wave it near a Coke can, the Coke can kind of goes towards it. It quite likes to stick to it and kind of roll around with it. So there you go. We've kind of built this kind of strange force field. We can attract the Coke can across the table. The question is, what is going on? So, Dave, why don't you tell us what's happening here?
Now, electricity is transferred by little tiny lumps, little particles called electrons. And some materials like electrons more than other materials do. So, and when you put a material close, two different materials next to each other, you tend to get a few electrons transferring between them, but not very many. But if you pull the thing away again, then those electrons get stuck in there. And then if you put it near another little bit which isn't charged yet and pull it away again, you slowly transfer electrons from one to another.
OK, so this is what's happening when you actually rub it, because it's coming into contact with one bit of hair and then immediately being pulled away again. And then when it gets rubbed back again, it's coming into contact with another piece of hair and so on. So it's kind of very inconsistent contact.
Yeah, you're touching a bit of hair, then releasing, touching a bit of hair, so you slowly transfer more and more electrons on, and it gets what we call charge. So you get polystyrene tends to gain electrons, and so you get slowly more and more electrons. It gets negatively charged, because electrons are negatively charged.
OK, then, so we've got this negatively charged piece of polystyrene. Now then, what happens when we wave it next to a Coke can?
Well, because electrons are negatively charged, and like charges repel, if you put it near the Coke can, all the electrons, because it's a metal, it can flow over the other side, so they all get pushed away, which means that the side of the Coke can nearest the polystyrene gets positive, and a positive is attracted to a negative, so it gets pulled towards the piece of polystyrene, and you can pull the Coke can like that.
OK, so there we go. What we're actually doing is we're making this piece of polystyrene charged by rubbing it on someone's head. And we've had some volunteers here who've been very willing to do that. And then, of course, because it becomes negatively charged, it gains electrons. That means that when you wave it near to this Coke can, and the Coke can is metal, you actually end up kind of polarising this Coke can. You get some charge pushed away down to the far end of the Coke can, and thus that means that it is attracted itself to the negatively charged piece of polystyrene. So in the end, then, you get this kind of attraction between the two, and you can drag the Coke can around without even touching it yourself. You can just drag it around with this charged piece of polystyrene. All right, guys, so Robbie then, how did you like that experiment?
It sounded fine.
OK, that's good. And yourself, Matthew?
Fine as well.
OK, well, thanks very much to you guys, Robbie and Matthew, and Hunsbury Park Primary School, and also to Dave for the experiment. So I hope you are at home making some force fields if you haven't done so already. All right, then, well, that's all from us. So back to the studio, and we'll be back for some more science somewhere in the east of England next week. Goodbye.
Well, that was Derek and Dave and what they did on their holidays. Next week on Kitchen Science, we'll be finding out how enzymes in your body break down food. So we can do this live in the studio. If you want to take part as well, all you need is a slice of bread and someone willing to stuff it in their face. So find out more by tuning in next week. And really quickly, we have a call from Ian in Northampton. Hiya.
Hello.
Hello, what's your question?
Well, I come from Dorset, and there's a village at Ashmore on the top of the Cranbourne Chase, one of the highest points in Dorset, and there's a pond up there. It never dries out. There's no negligible water feed.
You want to know why this is? We've got to be quick here.
It is, yes.
All right, Harriet?
Yeah, it's possibly a dew pond, and these have been constructed throughout much of the South Downs and other counties in the south of England, on the top of hills where, as the warm air rises, it then condenses, and the ponds are lined with clay, and the clay cools down, and that also helps when the air sinks to leave moisture behind, and a pond forms which farmers use for watering their animals.
That answers your question then, Ian?
Well, yes. It never even dried out in 1976 when we had that severe drought.
Well, that's probably the reason why. Anyway, we haven't got enough time, so thanks very much for calling.
All right, then. Thank you. Bye.
OK, thanks. Well, I asked you a question earlier, which is, what is the brightest star in the sky? And the answer is the sun. It's still a star. We've had a winner who is Roger in Marsham. And we also had an anonymous caller who said the brightest star is Dr. Cat. So flattery will get you nowhere at all. The winner of our fact and fiction is Mike in Malden, and he wins a copy of Dr. Chris's new book, Naked Science. And next week we're going to be back with our fossil, Dr. Chris, who is going to be talking about energy and chemistry. And we're going to be joined by Fraser Armstrong from the University of Oxford to talk about fuel cells, Emma Schofield from Johnson Matthey Technology to talk about catalysts. You'll need your slice of bread if you want to do kitchen science. Thanks very much to our guests, Lawrence Owens, Harriet Allen, Nick Brooks. Thanks to all the team in the studio. This is me, Dr. Cat, and Dr. Dave saying thank you, good night.